How do you kind of categorize what works and what doesn't work today in the robotics foundation model world?
There was a robot folding a shirt, and I was a little disappointed that it's slow and it still makes mistakes, and I see a full pile of full folded clothes. And that was just like, wow.
How do you think about the performance threshold you even need to hit?
For some tasks, it doesn't matter. You just need to get it done.
We sped up training by 10x.
That was one of those moments where it was like clear, like, holy shit, this is going to work.
What year do you think we'll have 1 million Americans with robots in their home?
You want to answer?
Physical Intelligence is one of the leading AI robotics companies. They've raised over $400 million and released a slew of fascinating research. Today on Unsupervised Learning, we had Karol Hausman, their CEO and co-founder, and Danny Driess, one of their key researchers, talk about everything AI robotics. This is a particularly fun one to do with a Redpoint portfolio company, and we hit on a bunch of different things, including what works and what doesn't in the robotics world today. We talked about what the key challenges are ahead for scaling these models and when they'll be widely distributed. And then we also talked about what it takes to run an effective research lab. This was the best conversation you could have in robotics with two of the best minds in the space. I think folks are really going to enjoy it. Without further ado, here's our chat. Well, thank you both so much for coming on the podcast. Really appreciate it.
Thanks for having us.
Thank you so much.
Yeah, I've been looking forward to this. I figured I'd start in the broadest possible way, which is that I feel like the two of you have been involved in like many of the seminal advances in AI robotics over the past decade, and obviously, things like RT2, PaLM, what you're doing now at Physical Intelligence. And I think our listeners would love if you could kind of just contextualize what has this last decade been like in AI robotics and how you think about the progress, and milestones.
So I've been in robotics for something like 15 years or so.
All right, you can do 15 years too.
It was really hard. There was lots of ups and downs, but I never felt that there was a light at the end of the tunnel. It always felt the problem is way too hard. And there were all kinds of ways to improve it, maybe for certain task or certain problem, but I personally never saw a path to like actually solving it fully and having robots out there doing all kinds of different tasks. That changed recently, and I'm happy to talk about it. But I think basically if I look back, the problem I saw back then is that it seemed like the world is just so complex that it's not possible to write code to let the robot operate in that world. And at the very beginning, like when I started, that was the predominant path to solving robotics. We'll just write the code that will explain to the robot what it sees. It will control the robot and move its limbs to accomplish tasks, and we will do it task by task, and eventually we'll have big enough of a library of these primitives or of these tasks, and we'll be able to handle this diversity of the world. And then sometime, I don't know, maybe 7 years ago or something like that, maybe 10, we started seeing these new wave of approaches showing that you can't really code the robots to do these things. You can't just like sit in your armchair and figure out all the different rules that apply. They need to learn it. They need to learn it the same way as we do. They need to learn it from their own experience. They need to experience the world, and they need to get the understanding of the world through learning. And initially, when it was starting, a lot of people were questioning that. It's kind of it's unsatisfying in some ways because it's not on us anymore.
Yeah,
it's more on the algorithms, on the robots to figure these things out. And there's a lot of things you lose. You don't understand exactly how the robot is doing the thing or why is it doing the thing. So there was a lot of pushback initially, but then over time, I feel like we're constantly keep on moving towards making it more learning-based and more end-to-end and more learn from experience. And then in the most recent history, which has been the most exciting to me, there's been many advancements over the past 5 years or so that really started pushing the needle and showing that these methods can really work. Some of these we were involved in. Maybe, do you want to talk about PaLM?
A good chunk of it. And I think also maybe contextualize like how many of these advances were directly tied to the advances that were happening in, transformer-based models, and how many of them were maybe independent of that.
I think one thing that is very different from how it was in the past. In the past, it was that people were trying to solve a certain robotics task, like one, let's say like
a Rubik's Cube maybe from a certain foundation model.
Exactly. And then you developed a machine learning algorithm specifically for that. And then you've done the project, you achieved a certain amount of success rate, and then you moved on and you developed a new thing, right? And when large language models started, it seemed that you can train a single model on many, many things at the same time. So the question is, can you replicate something like this in robotics? So can you train one model on many, many, many tasks at the same time? And so that you have one algorithm that the more data you collect, the more tasks it can solve. And that is what I think really has changed. And so maybe one of the first projects that we've been doing was this Palmi.
Yeah. Was it immediately obvious? You were both at Google at the time, right?
Yeah.
Was it immediately obvious as this progress was being made, on the language side, that like this would be applicable to robotics, or was there a lot of early data or experimentation there?
So if you just tried those models directly on robotics, they didn't work because language models didn't have any vision, right? They couldn't perceive the world. So that in SECAN, there was a way of grounding the model to the real world by having these controllers that could tell the model which can you run them or not.
Right.
And then in Palmi, we directly integrated vision into the model and trained it on robot data and also other data sources such that the model directly can perceive the world and make decisions. And that what was very, very exciting there was that, these people always say these are large models, and large models require so much data, but these models are very data efficient in certain ways because to learn a very hard task, if you have already good amount of pre-training, you actually don't need that much data, much less than if you had not a powerful backbone from which you can build upon. Yeah, so, and I think that maybe was a little bit an exciting moment when we did.
I guess it was kind of unclear whether it would just require such an amount of data that would be completely inaccessible.
Yeah.
For me, one other moment like this was this RT2 moment that where we run this experiment. That the specific version of the experiment that was really exciting that people know about is when we asked the robot to move the Coke can to the picture of Taylor Swift. And when you look at that demo, it's actually quite pathetic. You see this robot with a single arm, like barely grasping a Coke can and moving it like barely on the picture of Taylor Swift. I think it tumbles over. It's just like, it's not very good. But I remember when we saw this, it was extremely eye-opening. And that was one of those moments where it was like clear, like, holy shit, this is gonna work. And the thing that was in particular really exciting about this is, as Danny was saying, before our idea was that to make these models work the same way for robots, we would need to collect the same kind of data sets that people have for language. But there is no open
internet.
You need an internet of robot data. It doesn't exist. And that would take so much money and time and everything to do that. It's basically not possible. And what that result showed is you can actually take a pre-trained vision language model that has been pre-trained on internet data, has this web scale understanding of what's happening in the world, how the world works, and then add a little bit of robotics data, and these two connect. Yeah. And now the robot, even though it's never seen a picture of Taylor Swift before, it doesn't know what Taylor Swift is, it doesn't understand that concept. Now it can connect that concept that it got from the internet to the motion that brings the Coke can to the picture of Taylor Swift. So no longer the robot needs to experience everything firsthand. They can get some of that knowledge from the internet.
Yeah.
And
You're basically getting perception and reasoning like from the base model and then adding kind of the actuation side.
That's right. And you can connect it to motion. You can make this like very sophisticated connection between these two different parts that are very, very different. And the model can do it implicitly. And that was super, super exciting.
Yeah. I actually remember you. I think you were writing at the time, like, oh, we will all remember that moment when this happened. I think the first thing was actually grasping a fish, because there was never a fish in the robot data set. I think it was the fish, and like a toy fish. And this worked. Like the first time we tried it was like,
you can see how pathetic the tasks are.
I've definitely moved on to cooler ones now. I mean, I'm curious. So obviously you were doing all this really interesting and innovative work at Google. When did you kind of decide, hey, this makes sense to, do separately as a company or spin out?
Yeah. There were a few moments throughout where like things start to work, and I started thinking a little bit more about where that could lead and what would require to actually make it work. And one thought that I had is, Google is an incredible organization. They do incredible research, all kinds of different things. But I think this problem is so large and so complicated that to truly solve it, you need an organization that is fully optimized just for that. Yeah. Whose sole goal in the world, the reason to exist, is to solve the problem of physical intelligence. And that became very, very clear to me, very apparent. And that was the moment where, we still need to figure out if it's actually possible to start a company like this that will have enough resources, can attract the right people, and so on. But when it turned out that it is possible, it was very, very clear that this is necessary to solve the problem.
Yeah, and obviously you've had a quite the journey since then. I think it maybe would be helpful for our listeners. Can you contextualize like where are we today? So obviously you've made a lot of advancements in the last 9-12 months. How do you kind of categorize what works and what doesn't work today in the robotics foundation model world?
Yeah, so when we were starting, we were thinking of 3 axes that we thought were really important for these models. One was capability. Can we get these models to do tasks that we've never seen robots do before, that are really dexterous, really long horizon, really complicated? Then we thought that the next step would be generalization. How can we get these models to truly generalize the same way as language models do, that you can ask them something or put them in a situation they've never seen before and they could act correctly? And then the last one is performance. Can they perform as well as humans can with very high success rates, really robustly? So we started with the first one, with capability. And within the first 5 or 6 months in the company existence, with the Pi Zero released, we showed that you can get these models to perform extremely dexterous tasks like laundry folding, building boxes, bussing tables, all kinds of different things. You can do it across a wide range of robots. And it really works. You can get it to the point where if you can teleoperate something, you can probably get the model to do it. Then next, we started tackling the generalization problem. So can we get these models to work in situations they haven't been before? And that was our most recent release, Pi 05, where we showed that you can bring the robot to a new home that it's never seen before. And we pick a home because homes are the most diverse environments. Right. So it's kind of like the hardest version of that challenge. And it kind of worked. You can bring it to a new home and it can do long horizon tasks like clean your bedroom or make your bed or put dishes away and things like that. It doesn't work every time, but it works some of the time, and we kind of started getting better understanding of what it takes to get these models to generalize better. And now the biggest challenge is performance, is the third one. And that one is, I think, a little bit more uncertain. I don't think there is like a very clear solution where you just need more data or you need more diversity or something like this and it's going to work. I think it will require some algorithmic work, some new ideas. But that's more or less where we're at today. We need to get these models to perform much, much better. They still fail a lot. They're more like demo ready than they are like actually deployment ready. But I think we'll get there too.
Yeah, well, I will say, I think watching some of the videos, the performance on like shirt folding seems better than I can do already. So you're already off to a good start. How do you think about the performance threshold you even need to hit? Because obviously, I think one of the promises of this is, you could go to sleep and in the background, like these things are happening, and maybe it takes them 10 times longer than it might take me, but like that's actually a fine outcome.
Yeah, I think it probably will depend on the task. There are some tasks where it really matters how fast you are, how accurate you are, things like that. There's certain industry where failure is not acceptable, and there are some other tasks where it's totally fine, and you can take the whole night, and if that's what it takes to fold your laundry, you'd still be happy in the morning. I remember I had this one moment in the office where we have bathrooms right next to robot stations, and there was a robot folding a shirt, and I was looking at it, and as I was walking to the bathroom, I was looking at it and kind of being mesmerized a little bit how it moves and how it does everything. And I was a little disappointed that it's slow and it still makes mistakes. It was kind of like still the early version of the model. And I went to the bathroom, I come out and I see a full pile of fully folded clothes. And that was just like, wow, like it doesn't matter.
Yeah.
Right? Like some labor was done. Like it went from this chaotic, pile of shirts that was just like in a basket, in all kinds of different configurations, to now like fully folded pile of laundry. And that was kind of mind blowing. That was kind of like the moment where I like internalized that, like for some tasks it doesn't matter. You just need to get it done.
I think what's impressive watching so many of the demo videos is even when they do fail in some way, like they're actually like quite resilient in figuring out.
They're much more human-like than the robotic techniques of the past, where there if you make a mistake, you can't recover. Like you have to be extremely precise. You need to go to the exact point where you're supposed to go, and you just go there as fast as possible. These models and the way that robots look when they use these models is much more human. They make mistakes, but then they correct. They, will redo the task if they don't think they're good enough. Sometimes it's frustrating. It's a very different kind of robotics.
Yeah. Well, I'm going to ask you what I think is probably the most common like layperson question about robotics, which is everyone loves to draw the comparison to self-driving cars. And they're like, is this going to be the same journey? Is the last bit the hard part? That comparison, what works about it? What maybe is not correct?
So both of them are a very hard problem, and both of them, if they are being solved, have a huge impact on humanity. I think like if we can make a little bit of a thought experiment. So if you removed all humans and all other cars in the world, autonomous driving would be rather trivial.
Yeah.
I'm not saying it's 100% trivial, but it would be rather simple. For robot manipulation, if we remove all humans or all other robots, the problem would be as hard. So an autonomous vehicle has to make many decisions in real time when each decision could catastrophically influence the outcome. And the environment changes quickly in unpredictable ways. But an autonomous vehicle never has to interact with the environment. It never has to touch anything. It hopefully will never. Yeah. But a robot that manipulates something inherently has to touch things, and contacts make things exponentially hard. But let's say you knew that an autonomous vehicle could go from position A to position B. So like park there or to make a right turn. So if you knew that this was safe, then executing this motion is very simple. We know how to do that. But for in robot manipulation, if you know that, you just have to fold the shirt, that is still super hard. You cannot do it. So like it's fundamentally different in that regard. But of course, like if you think about the long tail performance, so like one big issue that autonomous vehicles have is that the long tail of things that can happen in the world is very, very diverse and very large. And to nail 99.999 or whatever accuracy, the long tail is the problem. And a similar thing can happen for robot manipulation, where if we want robots to be rolled out everywhere, there's a very large long tail. So I think these are the learnings and that are similar.
And I think the trajectory could be similar for this technology too, where with ChatGPT, with LLMs, it was kind of like all of a sudden it appeared, and like everybody was surprised, and it's like, whoa, like now I have access to this like crazy intelligent chatbot. And with autonomous driving, that wasn't the case. It was like a very long road. We were promised autonomous cars a decade ago or so. And it seemed like there was no progress being made. It's just going very slow. And then all of a sudden it's here. Like Waymos are here. You can take it anywhere you want in San Francisco. And I think something similar might be happening with robotics too. That it will be a long road, maybe longer than people expect. But there will be a moment where at some point like they're here. And it will be a very like a holy shit moment. Similar to what we experienced with Waymo.
And does it feel like it's a similar, obviously for the self-driving companies, a lot of it is just getting enough of this like weird long tail data. Like, the 99% of the stuff that happens when they're driving now isn't that helpful to them. And then like it's the really weird stuff that happens and they have to like amplify that through simulation. Like, do you think that ends up being a similar problem in robotics where like, it's that long tail of data that really matters?
So one thing that happens already is that on the scale that we can collect a lot of data and we can collect a lot of wrong data in some sense. So like,
I see you always messing with the robots in some of the demos.
But what I mean with this is basically if you just look at the number of data points that you have, this not necessarily gives you better policies. You really have to collect the correct data, and it's similar, I guess, like most vehicles that drive around. If you have this data, it's not very helpful anymore.
There's lots of parts of what you're building that are fascinating. I'd love to dive into a bunch of them. Maybe to start with just like the hardware side. Like obviously so much of the capabilities of what you're able to do with the models depend on the hardware. Even just like your data collection efforts depend on the hardware. What is like the state of hardware in robotics today? Like what works well for you guys? What are some of the pain points?
So to preface it maybe with a misconception that I think is fairly common, which is that we're bottleneck on hardware, like in general as a field.
Yeah.
I don't think that's the case. And there's this famous demo from more than 10 years ago from Pier 1, which is this very old robot that is roaming around the home and tidying it up and doing an incredible job. It would be like state-of-the-art humanoid demo today. And it does it just fine. And the caveat is that it's teleoperated. There is a person behind it that is using their own brain to control the robot. And I think that is a proof that hardware has been there for a long time.
Totally. I mean, to your point, anything you can do via teleoperation shows the hardware is fine, and then it's just the software side.
That's right. And we see it all the time. Like we can teleoperate fairly simple robots to do incredible things. So it's
like a lot of other robotics companies, that's their demos.
So it's very, very clear that The bottleneck is intelligence. Like if we had the same intelligence that a person has when they teleoperate a robot, we would have robots everywhere doing all kinds of different things. And I don't think they'll be bottlenecked on hardware. So I think that's kind of like the main point here. In terms of hardware in general, I think we see a ton of progress there. And the modern humanoid robots, all kinds of robots that are coming out now every day are extremely impressive. They're amazing pieces of mechatronics. I don't think they're the bottleneck. I don't think that's something that is really constraining us in the moment. But eventually, probably it will. So I'm glad that these efforts are starting and so on. But I think without the intelligence, we'll still be bottlenecked on that part.
And as you think about like milestones and intelligence, obviously it sounds like when you saw the Coke can Taylor Swift thing, you were like, this is going to be a moment we'll remember. Sometimes it's kind of, it when you see it and you'll make progress in the models and know something's a big moment. But how do you think about what like some of the other meaningful milestones are ahead where you might jot that down in the future?
The big one that we just achieved that to me was really significant was this generalization milestone, was bringing a robot to a new home. Because as Danny was saying, in the past, basically every robotic demo, including our own.
Very precise kitchen.
Very precise things. You have to collect data in the exact same environment and, don't touch the light switch. Like, if there's different time of the day, it might not work and everybody's okay with that. And we really wanted to move away from that and evaluate it in a home that it's never seen before. And there's so many other things than lighting and things like this, like small distractor objects that are different. Like you come into a new home and it's going to be very confusing. The tabletop is different, all the lighting and all the other stuff. The objects are in different places. There's so much understanding that you need to have to kind of know how to operate in that space. And with Pio 5 being able to do that, that was a really, really big moment for us, I thought.
Also, in machine learning, sometimes I think it's good to take a step back and think about what would be the best machine learning algorithm that achieves zero error on the training set. It's just a lookup table.
Yeah.
And in robotics, you fundamentally can't do that because you can never reset the scene to the same way, right? But still, a lot of people for a very long time had the feeling that, or the thought that if you train on your test distribution, the performance must be strictly better.
Yeah.
And I think one of the coolest things that happened in Pio 5, if you look in our paper, we have a plot showing that, is that if you train on a large or sufficiently diverse enough set of scenes, then you can achieve the same performance in an unseen kitchen that you could if you had data from the kitchen.
Right.
And I think that's just a very magical moment that you can achieve just the same performance, even though if you've not seen data compared to a model that has seen data in that kitchen. And I think that, for me, was a big moment.
Totally. It mirrors a lot of the magic of LLMs, right? Being able to do things that haven't seen before. And it sounds like the next set of milestones for you guys is really around performance. Like, is there something you think about, like, God, like when Pi, whatever it's going to be called, Pi 1, Pi 0.6, when it's able to do, this thing in performance, that'll be, kind of a step change.
Yeah, I think we kind of like go step by step looking at what is the bottleneck for really deploying these models widely. And, initially it was scalability, then like this generalization aspects, because it would be really hard to deploy it if, you change lighting and it stops working all of a sudden. Now it's clear that we are past those, or like we at least understand them enough. And now we really need to get them to work, really need to get them to be really, really robust. We are making a lot of progress. So I think in the past there's been a few indications of how this problem could be solved on small scales. There's a lot of research papers around, using RL for these things and stuff like that. I think the challenge is how do you create a recipe that you can apply to any task at scale, where you just have a little recipe that you just apply one by one, and every task is being solved one after the other, regardless of what hardware you're using, and all the other stuff. And that is still unsolved. So it's a little hard to predict what it will look like, what the recipe will look like, what the final result will be. But if the past is any indication of when this will happen, I hope it will happen soon.
Yeah, I guess I'm curious. Obviously, of the three things to get right in these models that you rattled off, it seems like you've got two of them relatively early in the company. Is that what you'd expected? Like, how does this compare what's happened so far to what you thought when you incorporated?
I personally didn't expect it at all. My timelines were way longer. And that's maybe something about me. I should be like way more optimistic about these things. I should change my model. But yeah, I thought it was going to take at least like 3-4 years until we get to where we are today.
What about you, Danny?
I strongly believe in the large model plus large data scheme. Right? Like there are many unsolved problems, and it's not like we can just this is it and we can walk. But like I knew that we haven't fully tried everything, so for me it was just carefully trying the things that we always wanted to try. And I think what was very nice though at Pi is like how quickly we could try these things that we always wanted to try. So that like I always had this hope that these things work out, but then seeing them work out faster than maybe than we thought, that's very nice. So, but like this is very often interesting that this is an old saying that ideas are cheap, but it is the way in machine learning very often the case that many people have certain ideas, but then to actually implement them in such a complex system with so many moving pieces, like real data collection, real hardware, real like different model sizes, real time constraints, all these things, and making it actually work. Like, there's still a lot of uncertainty, but seeing it coming together is very nice.
Yeah, we sometimes talk about how easy it is for LLM people, how jealous we are.
Yes, because they have the internet, or because
they have the internet. The evals are easy. You don't need to have any real robots. The data is just there. Well, their objective is basically the evil objective. There's so many nice things about it that we don't have in robotics.
Well, one thing I'm curious about actually on that line of just we're on this crazy exponential slope of LLM improvement right now, and obviously a lot of the LLM world is focused on getting models that are good enough at coding and ultimately AI research, and then accelerate AI research itself. I'm wondering like how that trajectory plays into the work you're doing, and if we continue on this like crazy exponential of LLM improvement, does that meaningfully change your timelines on the robotics side, or is there still like the cold hard constraints of the real world and hardware and data gathering that we could have the most superhuman coders and still it takes time?
Yeah. It's a little hard to say, to be honest. I think initially the hope was that in this moment with RT2, once we connected real world data to VLMs, it would be just we'll kind of attach ourselves to this bandwagon that once VLMs get better, we'll keep on getting better. I don't think we fully seen that yet. I don't think we're there yet where we can just take benefit from these models getting better and better. I think there is many indirect ways how we benefit from them. Models are getting faster, cheaper, the inference is better, all of those things. But I don't think we're right now bottlenecked on the underlying LLM being better. I do think that we see quite a bit of visual capability being a problem with what we do. So even if we have models, our models that can perform activities fairly well, you still need to command them usually with language what to do in the current situation. And we usually use VLMs, or we train our own VLMs, or fine-tune existing VLMs to do that. And if those were better, I think the overall system would work better. But I don't think that's the main bottleneck right now.
It feels like every few months we're probably learning answers to research questions that folks want to know. And I feel like in the robotics space, back in the day, there were all these questions around simulation data versus teleoperated data. What feel like the big outstanding questions right now that you're like, oh, if I could fast forward to 2-3 years and know the answers to that, it would be pretty helpful for our research today?
I think for me there are two. So the one is about generative video models, and the other one is maybe if the recipe is already sufficient, maybe I can expand a little bit. So generative video models, I think I did
your
not.
Former employer has some pretty impressive ones.
I did not expect them to be that good that quickly. I have to say, but if you try them on robotics team, they still don't work enough. And so I would like to know if.
Sorry, what does it mean to try a generative video model?
So let's say you put in a scene, you condition a model on let's say this table here, and then prompt it to move the glass to another location with a robot arm. The way the video will unfold very often looks highly unrealistic.
Yeah.
So the physics is very often not quite correct. These models make a lot of progress in physics, like in other scenes, but as soon as there's a robot in the scene, it's just not there. And like unfortunately, if we want to execute actions in the real world, tiny things like a millimeter off or whatever can make a huge impact. So I would like to know if generative video models overcome that and then become very useful for robotics, or if they if this remains a problem.
And if they did overcome that, if physics were suddenly, all working correctly in generative video models, would that like completely change the architectures you guys use?
So at least like a lot of the concerns of how to achieve generalization could be solved, like to new tasks, because you could just use the generative video model as a simulator,
right?
When you try to solve a new task in this particular scene that you are in. And try different action trajectories and see which one is the best. And if that generalized really, really well, I think that would not fundamentally change things, but it would provide a faster path towards generalization to new tasks in unseen environments.
Yeah. And then what about the recipes?
So I think, I mean, I don't know if it's true for LLMs or something, but it might have been that LLMs worked earlier than the inventors of them thought. And so I also wonder, when is there a point in robotics in which the stuff that we have works without us realizing? And works in the sense of that it's not necessarily a research problem anymore, but like still a very hard, but an execution problem. Right now, I think it's a scaling problem. Right now, I think it's still a research problem, but I would like to know.
So if someone could come from the future for like 2 years and just give you the enough conviction and just like,
exactly.
You got the recipe.
You got it. Exactly.
Just keep doing what you're doing. Yeah, that would be helpful.
Yeah. Are those the same questions for you or what?
I agree with the answers here. I think one other one that I would really like to know the answer to is some version of scaling laws, but I think usually when we think of scaling loss, we think of it in terms of the LLM scaling loss and how to pick the right batch size and how much compute for certain data and things like this. I think the scaling law that we are actually after in robotics is very different. As something as crude as dollars to model capability. And having some kind of monotonic scaling law of that and understanding the underlying recipe and how to translate one into the other. I don't think we are there yet, but I think if I had something like that, then again, it would turn just into an execution problem.
Right, the dollars being allocated to data collection, compute.
Whatever it takes, whether it's compute, data collection, whether it's compute for video models or something else. But having that understanding would be really, really helpful.
I'm curious, you're obviously, one of the first companies to really scale up, building these models, data collection. I'm sure you're coming across all sorts of problems that you're just solving yourselves. And it feels like over time, as the people from the future come and tell us what the recipes are, or you figure them out, there'll probably be, more and more folks going after this and building stuff. Is there a set of like infrastructure needs that you've come across where you're like, God, it would be really nice if there was someone else that was building this. It would make it easier for us and all future robotics companies.
Yeah, so robotics, because the type of data that we're dealing with is all time series data and it's multimodal, has multiple different camera views, the time series, and you also have robot states and actions, and then you have language annotations. These language annotations are also still a research problem, so you iterate a lot of them. So the data infrastructure that we're building, we all built in-house, and it's a real challenge to make this fast enough to just store it well enough so that you also can still iterate on it. And we have some custom requirements there, which are different from like static data sets that you just collect once and then they remain this way, because our data grows every day, right? Like it just grows every day. So I guess it might, for some people, maybe it might sound boring, but I would absolutely disagree with this. But like data storage, data pipelines, and so forth, that's a very important infra problem.
Yeah, that's one thing maybe that I underappreciated coming into this, like how much data robots generate.
Yeah.
Like we knew it was going to be a lot, but like it grows quick.
Yeah.
It's a lot. And it's also like everything they collect is ground truth in some way, right? Like it all tells you about how the world works. Even if you fail at folding laundry or something like this, it still tells you that if you move the arm this way, that's how the shirt is going to deform. Which is not the case with LLM. There's some data that is just like wrong.
Yeah, you like take that out of it.
Yeah, just bad data. The amount of data we are dealing with is kind of crazy. I think the other aspect that would be really nice for someone to solve, that we are trying to solve in-house, is how do you decide what data to collect and build all the machinery around understanding that, understanding the quality of the data you collected so far, How do you do quality assurance at that kind of scale? How do you do language annotations in the right way at that scale? How do you know how much more data is needed for the model?
Yeah.
How do you know what strategy to use to collect that data? How do you train people who are actually collecting that data to do this at scale? So all the infrastructure around that, on managing the performance of this, on understanding that data, on being able to look through all of this all at once and have like a bird eye view understanding of like this is how my data set is, more or less. That would be really, really helpful.
Yeah. How do you know what data to collect? Why start with folding shirts and picking out dishes and how do you pick the tasks?
Right now, we pick them just to move as fast as possible. So pick tasks that are really, really hard. If you can fold laundry, you can probably assemble iPhones and do many other things. It's just like really, really complex tasks that we don't think people were able to do in the past. And then we pick tasks that are easy for us to understand, easy for us to deploy robots to collect data for, and things like that. So, every one of us has a home. We all folded laundry before. We know what a successful folded t-shirt looks like. We know what a clean kitchen looks like. It's much easier to do it that way than to work with a manufacturer, for instance, and understand their process, get on their schedule, get all their parts over. That could be expensive. Understand exactly how it should be done. So we just want to be trading very, very fast. And because the technology is very general purpose, we think that it's going to then apply to all the other tasks as well.
Maybe one thing to add here is that when we talked about the Taylor Swift moment in the beginning, this work got criticized by a lot of people saying like, oh, you could just run an object detector and then run. And so we could use a very similar technology now also to solve folding laundry. And it's very clear that you just cannot apply the same, like an object detector and a trajectory planner to fold laundry in the same way. So that's also one way of picking tasks which push the boundary of the capabilities and still convince ourselves that we have the tools to still solve them.
What's the intuition you use for this task is going to be hard for a robot versus easy?
I think it's hard to describe it. I don't think there's a checklist of if there's a frontable object, hard. If you've never seen before, hard. I feel like there's just a sense that you get over time as you work on the problem. For me, when we set goals and we talk about certain tasks, you can look at the faces of people in the room and how terrified they are. We need to fold laundry. That's impossible. There's some things that just robots they're quite counterintuitive that robots are really bad at. These things usually involve things that are not the same every time. So for instance, if you pick laundry out of a laundry basket, the shirt is always in a different configuration. You've never seen the shirt in the exact same configuration that you've seen before. And that makes it hard. That kind of the initial state distribution, the variance of that makes the task really, really hard. If the task is very long, that makes it hard because these errors can compound and that could be hard. If it's very precise or if there's some bottleneck during the task that makes it that is very precise, that's a hard task as well. But I could try to list some of those, but I don't think I'll be able to capture all of these things.
Yeah, an intuition from having worked with it so closely. I mean, similarly, I'm curious whether it's intuition or science at this point, evals. How do you know when these models are getting better? There's no SWE bench, I guess, in robotics world.
Yeah, evaluations are very important and a very hard problem. So the interesting thing is, I think I said this before, you can never reset the scene to exactly the same way, right? You just cannot repeat that. And so we just have to run enough evals, run statistical analysis if the numbers that we get out are statistically significant. And one thing that we also learned is that to really show that a policy is better than another, it's very often important to run it on many, many different tasks and many, many different environments. And then suddenly you might see differences. But evaluations is maybe one of the the hardest.
You're just like, oh, that shirt looks pretty crisp when it's folded. Or like, how do you actually?
Yeah, so we have like guidelines of the operators that run evaluations to how they should rate it.
Okay,
and
so
then
the operators themselves evaluate the.
And
what literally how crisp is the shirt. That's
Nice.
And what we also do is we never really compare absolute performance on this day to absolute performance on a few weeks ago, but rather we always run the baseline and the new model at the same time, run with the same operator, and then look at the relative ranking. I mean, there are some tasks that we have sufficiently understood for which we also look at the absolute performance, but just done to account for even just like lighting changes or like the robot has changed and it's a different operator who is much more picky about a shirt than another one.
Right.
Yeah. It's also that the trends for this are not very good, because as these models get more and more capable, we need to evaluate them on more and more tasks and on more and more robots too. So you kind of need to run more and more evals to get to an answer whether your model got better or not. So it is a problem. It takes a long time. It's operationally very heavy. There's a lot of variance in them. That's one of these other places where we're really jealous of LLM people. But there are some things that we're exploring to try to overcome that issue, other than just operational excellence, try to do this really, really well. You can start using simulation for these kind of use cases, video models, things like that. People have been investigating this for a while. We haven't seen them be robust enough yet to reduce that variance, to give us more confidence that this model is good. But there is some hope that they will get there.
Yeah. Well, talk a bit about like the role of simulation. Because as I understand it, one of the early bets you guys made was there was, some people have tried to go the pure simulation approach. You guys have really leaned into the teleoperation side as being a necessary component of the data recipe. Maybe talk about what drove you to that decision initially, and then how you think about the role simulation plays in this going forward.
Yeah, I personally spent quite a bit of time on simulation in the past. And especially recently, simulation has been extremely useful for robots, especially for locomotion. And I think the reason for that is locomotion, or like walking, is mostly around modeling your own body. If you can model your legs correctly, then you can simulate them on all kinds of terrain, and then you'll be able to transfer that to the real world and then walk properly. I think for manipulation, the difficulty is not in modeling your own arms. The difficulty is modeling everything that the arms are interacting with.
Right.
The problem is not how I move my arm from A to B, is how do I manipulate the world around me. And that is much, much harder to get right and much less scalable. So I do think that simulation is going to play a role. I think the kind of the entry point for it is for evaluations. If simulation is not useful yet, is not like fully accepted as the evaluation tool for these models, then I don't think it has a ton of use cases beyond that.
Yeah, that's like the first.
Yeah, that's kind of like the first gate that you need to pass. And once you're past that, then I do think it might really, really help. I also suspect that it will be more helpful the more diverse your real data is. I think if you are just collecting small real data set on a single robot, maybe for a single task, and then you have the simulated data set that is, very, very different than the data that you collected, it will be very hard for the model to kind of reconcile the two. Yeah. But I think the more diverse your real data is, the more simulation feels just like another version of reality that the model can incorporate and kind of not separate them into two different corners of the space. So I do think that collecting large-scale real-world data is going to help with that if we were to use simulation later on.
Yeah.
And I also try to not be dogmatic about these things. Like, so far, simulation has not been sufficiently good as a data source. But maybe if that changes in the future, this is the beauty of the type of models that we're dealing with, is that they could just be trained on all of this at the same time.
Yeah.
Yeah, that's right. If at any point we see that simulation is the way to go, we'll switch everything.
Totally. I'm curious about this because I feel like in the AI world, it's like, all these strong opinions loosely held because the world changes so fast and all these things develop. I'm curious what that means for physical intelligence of the company. Like, how do you, kind of allocate research resources or and prioritize things based on, I'm sure you have some more concentrated bets, but at the same time, exploring lots of things is probably really beneficial to furthering it forward. So how do you think about that from the company level?
It's hard to do. It's hard work. I think it's hard for any organization that does a lot of research. How do you find the right trade-off between exploration, exploitation? How do you, make enough bets but also have enough resources behind each bet for it to succeed. We do it in a few different ways. I think the main thing there is that I don't think there is a single recipe that is just like, this is how you run a research lab, and this is how you do it, and this is how you decide where you bet. I think it's mostly a matter of taste and belief, and having just really, really good people, researchers that do have taste. And I think if you look at the past, that's often what happened where breakthroughs came through. There was just like researchers that had enough conviction, enough belief, and they just happened to be right. So that's what we try to do. We try to hire the best researchers in the world that work on this problem, researchers that have the right taste, that can distinguish these ideas. And then we try to give them the resources they need to explore these things, and try not to do too many of these things at all times, so that we have enough resources behind each one.
How do you tell if someone has taste? Obviously, past performance can be indicative of the future, but I know you hire a lot of really young, talented people.
Yeah. How
do you get a sense of that?
It's a good question. I think the past can be some kind of indicator. There's only so many papers or research results that made a big impact in the field. There's so much research happening. There's so many papers, no one can read them all these days. So the probability of you having an impactful research result is actually fairly small. So if you have people that have had that multiple times,
sitting across from two of them, but yeah,
if you encounter people like this, then that means that they are doing something right. They're thinking about the problem the right way, or they are deep thinkers and they can change their opinions and they have the right taste. So I think past here could be some kind of indicator, but it's really hard.
So I think on our interview process, we really make sure that a lot of different people in the company are exposed to a candidate, and then I think if you have multiple people that have different styles of interviewing, interaction with people, I think you get a good sense of the alignment, and then the way we discuss it very openly and very, very fairly. I think I think so far we always I don't think we made any mistake in hiring so far, so that feels very, very good. We were all very aligned.
Yeah, there's also some soft skills maybe there. Like people who are not super dogmatic, who can take new evidence and change their opinions, who let science lead the way. Who are willing and who are very open-minded and willing to try something that, even though they don't believe in it, but they think that it could be something that they want to try. Lots of these things that are I think are difficult to put your finger on, but you know it when you see it.
Yeah.
But one thing that comes to mind here is that I like interacting with people that are just willing to do the work, and not say, oh no, I don't want to do X, Y, Z because I don't know, for whatever reason, but just to do whatever it's needed to achieve a certain research goal, and I think those are the people I like interacting with.
Yeah.
That even let's say you've never worked on a data pipeline, but now for your problem you need to figure out a data pipeline, and you just go into it and do that. And I'm not saying, oh no, it's not my role or something.
Right.
Yeah, that's I think a nice property.
Yeah. Another part of your research strategy I'm curious about is you've open sourced Pythera, you are published a lot of research. How do you think about what you want to open source, what you want to kind of the insights you want to share with the world? Obviously in the LLM world, I feel like it started kind of open and it's gotten much more hush hush about what folks are doing. How do you see that?
Yeah, it's a very deliberate choice, and I think if you're too long on Twitter these days, it might seem like robotics is about to be solved, and it's just a matter of collecting a little bit more data, and all of this is going to be out there, and we'll have humanoids in the home today doing everything for us. And we think that we are still very, very early. There are still breakthroughs to be had. The technology is not there yet, and the biggest risk for us as a company and for the entire field is not that someone is going to get there first before us, that we're going to get outcompeted by somebody else. The biggest risk is that we're just going to fail. Science is not going to cooperate, and we're not going to solve this problem. And then it doesn't matter, whether you shared your results or you didn't, or what your strategy was, what kind of robot you were building. So we want to make sure that doesn't happen. And to burn down that risk, you want to make sure that you expose these ideas to as many people as possible and kind of invite them in. because we do believe that the path we're taking is the right path to solve the problem. So the more people kind of subscribe to it, get to play with these models, get to understand where they are going, get to contribute to them, the more likely it is that we're going to succeed. Not as just as the company, but also as the entire field, and the likelihood of solving the problem is higher. It might change at some point, once it's very clear that the problem is getting solved. But I think so far it's been very deliberate and extremely successful for us, frankly.
Yeah.
Like, it's also really helps with recruiting, for instance.
Sure.
People want to share their work. They want to make sure that, they can talk to their friends about it and get more people to help them with them. Also seeing just the impact of open sourcing these models, of Pi0 being used in so many different...
Yeah, what's your both favorite way it's being used?
Oh, I've seen so many, I've
Drones.
seen some weird, drone was
Drones.
super crazy. Drone being pre-trained on Pi0 and grasping things was kind of crazy. I've seen it on surgical robots. I've seen it on autonomous cars. I've seen it on so many different tasks that I didn't even think that Pi0 would help on. So that was super cool to see. That's really cool impact to be able to deliver.
And also, I think robotics very often has been, you show a video and then no one really knows what it is.
Right.
Just being putting it out, putting the model out for people to use. It's also a good way of learning how this could eventually be done for as a real deployment, and seeing how the models react with other players and so forth. So there's a tremendous value in that.
Yeah, it kind of speaks to this problem of evaluations with robotics. It's very hard to compare, is this model better that this team published on, or this other one? There's kind of no way of doing this well. There's no established benchmarks, and even if they were, if anything changes, the variance is so high that you can't tell. So yeah, I agree. Just putting it out there and letting people use it.
The same thing's been true of the LLM space, right? In many ways, the evals are kind of only so helpful, and it turns out users will tell you which models they like better.
That's right.
And what I also I think when LLMs came out, people didn't really know what people all can come up with, and I'm looking forward to the same happening in the physical world also. I want to be surprised what applications people come up with the tools that we're building.
Well, I want to dig in a little bit to some of the research you guys have been doing. I mean, obviously, you've had some really interesting work on kind of, training these models faster, right? And getting both faster, lowering the cost of it. Talk to our listeners a bit about that problem space and some of the stuff you've been working on.
Yeah. So when we build a robot foundation model, we usually start with a pre-trained vision language model. And I think we talked about this earlier, can we just when the vision language models get better, do we benefit from it? And so far it has been that the vision language model itself is not yet adapted to robotics. So the features that it has, the visual features, are not good enough yet for robotics. So we have to fine-tune it on our robotics problem. But when you do this fine-tuning, so you take a vision language model backbone, and then maybe you add certain new weights to it to make it output robot actions. And then if you fine-tune this only on the robot data, what happens is that the model does lose some of its capabilities. So it's not a good VLM anymore. And this has multiple effects. On the one hand, it lowers the generalization capability of the models. And in some sense, the model forgets a lot what it has learned in the internet. But also the training dynamics is not as good, because it has to change so much that it might train very slowly. And so what we've been doing is figuring out how can we fix this. And one concept that we came up with, we call knowledge insulation, which is the idea of it's a multifaceted concept. So we try to basically modify the training recipe to maintain most of the model's capabilities. And how we do this is we still train the model on web data, so non-robotics related data. And that helps, and that especially helps also for generalization. But that's not the only thing. The other important insight is that for the best performing recipe right now for building robot models is to use flow matching or diffusion as to produce robot actions. But it turns out that if you use this to train the model backbone, it trains very slowly. And the gradients that you get, they kind of destroy a little bit the backbone, even though you're using other sources. So the idea that we had is we can train the VLM backbone with tokenized actions. So we take robot actions, convert them into something like text, and train it this way. And it turns out that this adapts the VLM to robotics in a way that without losing its capabilities. And then we can bolt this action experts with flow matching on top of it and let them not communicate that much with each other, so stop the gradient and then have very good action prediction while still adapting the backbone. And the cool thing about this is I think we sped up training by 10x.
Wow.
And also generalization. So that has been quite good. So we cut our iteration speed much down, because that's something I also maybe for viewers to be aware of in robotics. Like you collect data, which takes a while. Then you train a model, which can take multiple weeks, and then you have to run real robot eval. So until you get a signal of where my decisions in any of this pipeline sensible, it can take a very long time. So if you make any of these stages faster, your research is not only accelerated by this amount you change, but by a much larger factor, because it can make your decisions much earlier.
Especially what we were saying at the beginning regarding the data. If only we knew what data to collect.
Right.
Like right now we only know.
Faster on that.
Yeah. Right now the only way we know is by training a model on that data. Waiting all this time, incorporating all of the data, and then running an eval, and that also has some variance. So if there was some way of figuring that out way earlier, maybe even without training the model, that would be super, super helpful.
I mean, another part of the research that I think you did very recently was making these models work kind of faster at inference, right? Where there's all these dynamic things that happen in the real world that you might need to, in a split second, make an adjustment or make a decision. I mean, talk about some of the latency issues that happen with these larger models, how you go about solving that, and is that all going to be algorithmic, or is there actual hardware needs that you'll have there?
Yeah. So we had a recent work from Kevin Black from our company who worked on this. So one thing that maybe to explain how these models are being queried, you get an observation and then you start querying the model, and the inference can take a few hundred milliseconds. And during that time, the assumption is that the world stands still, at least. But this obviously is not how the world works. So the world could have moved on, right? So what you might think of doing is, let's say you query the model based on the current observation, and then you always, so we never predict only one action. We always predict a whole action trajectory called an action chunk of what the robot is doing. So maybe you should just continue predicting the old action chunk, but while the inference of the model is happening. But then one issue that arises, it could be that if then the new action chunk is ready after the inference time delay, is that the world might have changed, or like that this new predicted action chunk is not consistent with the old one. And so Kevin figured out a way of using techniques from image inpainting. So like the diffusion models for generating images, you can like remove a patch and then they just fill in the patch again, as inpainting. Can apply a similar technique to basically impaint the rest of the trajectory given the one that you already executed. And that is a purely algorithmic advancement. You don't even have to retrain the model for it, as you can just afterwards apply it. And it worked really nicely. So to basically what happens is that the model is still, or the system is still executing an action while it's now computing the new action for the future. And then they're kind of like fused together. This is, I think, a way of thinking about it. But then, as you said, as an alternative, we would greatly benefit from advances to make like models much, much faster at inference time. That would also solve a lot of problems. This is something that we currently haven't really looked into because we've solved it in different ways. But
that's fascinating. I mean, taking something from filling in sparse images feels like the definition of like research taste. Like the fact that you figured that out, like that's
Kevin has very good research.
Incredibly impressive. I mean, I'm curious. You're obviously building these generalist models, and maybe just paint the vision of I imagine in the future, there'll be some sort of like task-specific post-training that people are doing on these models. But like, what do you think that if this works, what does that look like in 10 years?
So I hope, at least if I'm successful, is that there's no post-training.
That sounds good.
Okay, maybe a bit more. I'm actually serious, but maybe more towards your question. My hope is really that we provide better and better base models that are more steerable and more promptable, so that they could get a task to a certain amount of performance and a certain speed in whatever task. It's similar. large language models nowadays, you don't need to really post them when you give them to a user. They mostly work on, at some point there were like these APIs to fine tune models.
Right. Those with RFT, they're kind of back, but with a dozen examples, not some massive amount of data that's required.
Yeah, that's right. But what I can see is that if you want to squeeze out the last % of performance, speed, reliability, there will be very efficient fine tuning that you can do like on a weekly basis, even like collect like data for 10 minutes, feed this back in, and figuring this out. I could see that version. So the base model gets better and better, but there was always like this last percentage performance squeeze out. That's
and we start seeing some of this in our latest research. Initially when we wanted to get these tasks to work, especially these complex tasks like folding shirts, we always had to do very specific post-training procedure, and it required like quite a few people to like figure out exactly what the procedure should look like, and all the details in the procedure really, really mattered. But now, as we get better and better pre-trained models, we realize that some of them do work zero-shot just as well as the old post-trained models. And that is super cool to see. That's like exactly what we saw from GPT 3.5 to 4.
Right.
Where like all of a sudden this whole paradigm has changed. I do agree that I think post-training is there to stay. It's a little unclear whether it will be, you collect a few more demonstrations, or you just tell the robot a little bit more, you guide it in some way how to do the task, or maybe the robot explores on its own. I think it's still to be determined, but I assume that there's going to be a little bit of guidance that you can provide that will lead to faster execution or better performance at the end.
Well, this has been fascinating. We always like to end our interviews with a standard set of quickfire questions, which are overly broad and just stuff everything else into the end.
Perfect. We love these.
Maybe to start, you guys are so close to the cutting edge of AI research. I'm wondering, what's one thing you've changed your mind on in the last year?
I think for me, it was seeing this like environment scaling curve of you can achieve the same performance in unseen environment as if you had training data from it. I think it really has changed my mind.
Did you think you thought that would just take longer, or were you not actually?
I thought I thought that would have been a gap, or like that you need more diversity. Yeah. So I mean, we've talked about that the world is so incredibly diverse, but maybe it's actually like feasible. Maybe it's not that diverse, so it's feasible to kind of cover it.
We had these conversations before we started the project, like how many homes would it take to see before you generalize to the next one? And like the numbers that were thrown were like 1 million. Like, I don't know, like homes are so different, right? Like, and then it turned out to be 100, which is like still kind of mind-blowing to me. Yeah. Like it does seem to indicate that maybe we're giving too much credit to how diverse the world is. For me, I fully agree with that. The other one would be video models. I think they've made a ton of progress way faster than I expected. I still remember playing with them a few years ago and seeing all kinds of different problems with them. I think they're getting very, very good, very, very fast.
Yeah. And does that change like the, some of the research directions within physical intelligence today? Or is it like you're still waiting to see how much of a physics understanding?
We are definitely like looking out. We are definitely starting to explore them. We're trying to see, where they can help and what where did they change and how to make them more steerable and things like that. I don't think they got to the point yet where we are, completely change our research agenda, but we definitely are paying attention.
What's one thing that you feel like is overhyped in the discourse around AI and robotics, and one thing that's underhyped?
I think hype in both directions is always good because it draws people into. I'm sorry that I give a non-answer. So it draws people into like the things that a lot of people work on. A lot of people should work on because apparently they work. So hype there is good, and things that are underhyped means also that people that like finding more niche problems are also working on. So I don't want to even put names on these two things because I like things being over and underhyped.
Yeah.
Let's see. I think underhyped generalist robotics models. Nice.
Yep. I'd be worried if you said overhyped. So.
Yeah, that's right. Heavily overhyped. I think if it works, and so far, all the signs seem to indicate that there is something to that idea, that will fundamentally change how we think about the physical world and the intelligence in that world. Overhyped, and the other thing, underhyped, Waymo.
Yeah.
Yeah,
it really is.
It's absolutely
crazy. It's like the most visceral demo you can have.
It's absolutely crazy. Yeah. Like when you walk in, when you sit in Waymo, it's just like a very different experience than if you had the most intelligent chatbot. It's just like so visceral. Yeah, it's crazy. Overhyped. I don't think there are many things overhyped actually these days. I think maybe the craze around humanoids is like a little too far, I think. And to me, it mostly comes from this misunderstanding of like how AI is going to evolve, that for these models, it doesn't matter if it's, this kind of robot or that kind of robot. It can take the data from all the different form factors and generalize across all of them. And it will be the most general purpose thing that you can apply to all the different specialists.
Yeah. You don't think the world's been
robots.
optimized for the human form factor?
I've heard that.
Yeah.
I think, I mean, there is a point to that, but I think it's kind of like thinking that it is true. So therefore, let's build a robot that looks like a human, and that will be the robot that will see the most diverse data.
Yeah.
But I think you can go even further and say, well, like actually to these models, it doesn't matter what robots the data come from. They can take data from all kinds of robots. It could be cars, it could be drones, all kinds of things. And that would lead to even better capabilities of these models. So I think if you go with that argument just a little bit further, you end up in the world where you have a gigantic, big foundation model that powers all the robots, some of which are humanoids.
Yeah. All right, you ready for a really shameless podcast question?
There we go.
What year do you think we'll have 1 million Americans with robots in their home?
I think we already have 1 million Americans
with
robots.
with robots powered by some folding laundry and doing all these things.
As I said, I should be more optimistic about my predictions given the past progress, how mistaken I was. I think we'll see robots being deployed doing things that we've never seen robots do, probably this year or next year, if we continue on this trajectory. When they will be deployed in a home doing all kinds of different things, I think kind of the conversation has changed from never, or like the problem is fundamentally unsolved, to like somewhere between 5 to 10 years or something like that. And I think most of the community agrees that these are the timeframes now. I think if the progress continues and we're successful, and I think the progress has been speeding up, then I think it will be within the next 5 years.
You must think a lot about the implications of this model improvement and what the world will look like when these are deployed. And obviously, as you mentioned earlier, we in some ways have no way of knowing like all the amazing ways these models will be used across the board. But is there some prediction for the future when these things do work that you have that you think we're like not thinking about enough today, or is like maybe a weird or under discussed implication of the of these models being available prolifically?
I thought maybe to like turn it around a little bit, for software, I did not expect vibe coding to be a thing. And it's super cool.
Yeah.
We have like non-technical people in the office doing incredible things, building tools for themselves, like being extremely productive.
What are they vibe coding?
All kinds of different dashboards, all kinds of different tools for operations. It's super cool. And I was thinking the other day, what would vibe coding look like for hardware? Where you can just prompt the model, the intelligence is there for you. As soon as you create something, you kind of just like breathe intelligence into it. It's more the world that we know from cartoons, where like the hard part was making the thing, but like as soon as you make it, like it's alive. and I think that's going to be a very crazy transition.
Yeah, that'll be nuts when you can create any piece of hardware and then infuse it with these models.
That's right, and you breathe intelligence into it.
I think I would largely agree. I guess I'm wondering what people like. I really look forward to a time when there are no chores anymore in a home. I think like a lot of people would look. That's also interesting. Like I think if you think about ChatGPT or the ChatGPT moment or something, I guess one aspect of this was that a lot of people have never heard what a language model is, and suddenly the whole world knew what a language model is. But if I show anyone a robot video, then they always say, "Oh, I want this instantly." So they already have like a very clear conception of how it would change their life, which I think is pretty interesting. But I'm very curious what then people will do if they have never have to unload their dishwasher anymore.
Yeah.
Like what will this enable humans to focus on? Which I think would be very exciting to see.
I have a 1-year-old at home, and I was just watching myself all kinds of stuff I need to do around the baby just to spend more time with her.
Yeah.
And it's just crazy amount, sanitizing bottles, cleaning this, cleaning that, loading and unloading dishwasher, all of those things that like I don't want to do. I don't want to spend my time on this. I just want to have more time with her. So not having to do that and just have the home in the state that I want it to be in at all times would be pretty cool.
When she's older, are you gonna give her a chores list, or is this a moot point now that we'll?
Oh yeah, that's a good point. I need to think about that. I need to slow it down.
Well, this has been a fascinating conversation. I'm sure there's all sorts of things folks listening will want to learn more about you two, about physical intelligence. So I want to leave the last word to you both. Where can folks go to learn more about what you guys are doing, and any research or jobs pages or anything you want to point folks to? The floor is yours.
Yeah, you should check out our website. It's pi.website. There's
Who has pi.com?
I think it's up for sale, but it's like super expensive. We'd better spend that money on compute these days.
Fair.
And you can see all our blog posts or all papers. We're fairly open. We not just publish videos, we publish the full write-ups. We also open source our models. You can find them there. And we'll continue publishing research there. So keep following us there. Check us out on Twitter as well. And yeah, follow us. You should stay in touch.
Also, you can really write us an email. There's research at physicalintelligence.company. We will answer, and we always like hearing what people think about our work and how they think it could impact their lives and so forth.
Amazing. Well, thank you both so much. This has been super fun.
Thank you.
I enjoyed it a lot.